Hi guys, welcome back. Let's now look at a very important concept called CAP theorem. Almost any NoSQL conference you go to or any interview you attend will talk about this concept. So let's look at what it is and what it's advocating. The CAP theorem was first proposed by Eric Brewer of UC Berkeley in 2000, and it states that any distributed database has to choose between two of three requirements. The three requirements being consistency, availability, and partition tolerance. These three requirements are shown represented on the three vertices of a triangle, and we can choose any of the three sides. Therefore, we can pick availability and consistency, or availability and partition tolerance, or consistency and partition tolerance. You already know what consistency and availability means from the previous lectures, so let's look at what partition tolerance means. Partition tolerance means if your database is spread out to different machines and if there is a network failure, the system continues to operate. That is, it is able to tolerate network outages that snap communication between nodes. Traditional relational databases like Oracle, MySQL, etc. choose consistency and availability, while databases like Cassandra, Couch Database, Dynamo choose availability and partition tolerance, while databases like HBase, Redis, MongoDB chose consistency and partition tolerance. So what does it mean to implement two of these requirements? Let's look at each of the three combinations more closely. Let's first look at databases that implement availability and partition tolerance. These databases usually shard or distribute the data, and they're usually masterless, with every node being equal. Cassandra is a good example of this. Let's look at a use case where there is an overnight batch job that writes data from a mainframe to a database, and then this database is read throughout the day. If we were to read the data as it's being written, then we will get stale data, so consistency is sacrificed. But since this is a read heavy, write once use case, I don't really care about reading data immediately. I just care that once the write has happened, I can read from any of the nodes. So what would happen if one of the nodes were to go down? No big deal, as I will be able to read it from the node that's up. The system as a whole is available. And that also means that it can deal with network or partition failure between nodes, as other nodes will step up and handle the additional responsibility. Next, let's look at databases that implement consistency and partition tolerance. These databases also usually shard or distribute the data, but they tend to have a master or a primary node that can handle the write requests. A good example is MongoDB. So what happens when the master goes down during a write? Usually another master will get elected. Until then, data cannot be read from the other nodes as it's not consistent. Therefore, availability is sacrificed. But if the write went through fine and there's a network outage between nodes, it's not a problem, as the secondary nodes can serve up the data. So partition tolerance is achieved. Finally, let's look at databases that implement consistency and availability. These systems don't typically shard data, and they tend to have a master-slave architecture with data syncing from master to slave. If everything is fine network-wise, the data is consistent and is always available, and everything is hunky-dory. But what happens if the master is down? Since it's a monolithic application on one machine, if the database is down, it's considered down until standby is ready and traffic can be diverted to it. And what happens if the network link between master and slave is also snapped? The slave will have stale data, and since consistency is paramount, the database will error out. So it's not very well suited to modern big data use cases. That concludes my lecture on CAP theorem. Hope that was useful, and you guys can appreciate what the CAP theorem is trying to advocate. See you soon.